Welcome back. Today, we are going to dive into a fascinating problem in the world of artificial intelligence. How do we know if an AI is telling the truth about how it makes decisions? We will be exploring a brilliant research paper titled SpaCE-VAE, Sparse and Confident Explanations Using Variational Autoencoders. This paper challenges the very foundation of how we evaluate AI explanations and proposes a beautiful mathematical solution. To understand why this research is so important, let's first look at the paradox of the black box. Deep learning has achieved extraordinary things, but at their core, they remain mysterious black boxes. The field of Explainable AI, or XAI, was born with a grand ambition: to provide trust in these models by revealing their inner workings. For images, the most common approach is creating attribution maps, highlighting which pixels matter most. Current methods can highlight regions that look reasonable to the human eye. But how do we know the model actually thinks that way? Scientists often use feature ablation. The idea is simple. If a pixel is unimportant or has a negative contribution, deleting it shouldn't stop the model from recognizing the dog. Sounds logical, right? But here is the paradox. When we erase the useless pixels, the model suddenly predicts this dog is a cat. Why? Because by erasing the background, we inadvertently destroyed the contrast that defines the shape of the dark-furred dog. A flawed evaluation method leads to flawed explanations. To achieve this, the authors outlined 4 pillars for a perfect explanation. It must be accurate, sparse, confident, and interpretable. Their solution? SpaCE-VAE, an elegant framework built upon a vector-quantized variational autoencoder, or VQ-VAE. Let's dive into its architecture. The architecture consists of 3 main components: an encoder, a discrete dictionary, and a decoder. Together, they act as a sophisticated filter to explain a target classifier's decision. It all begins with the encoder. When we feed our dog image into the network, the encoder compresses it into a latent representation, a continuous matrix of numbers, which we'll call Z_E. In a traditional neural network, these continuous numbers flow directly to the next layer. But continuous spaces are infinitely vast and messy, making it extremely hard to extract distinct, human-understandable concepts. This is where SpaCE-VAE radically diverges from a vanilla VAE. Standard VAEs sample from continuous Gaussian distributions, which often leads to blurry reconstructions or the infamous problem of posterior collapse. SpaCE-VAE, instead, introduces a discrete dictionary, a finite set of embedding vectors representing solid visual concepts. Think of it as a limited palette of Lego bricks used to reconstruct the image. Now, watch the magic of quantization. For every continuous vector inside Z_E, the network searches the dictionary for the closest match using a simple distance formula. Once found, the continuous vector forcefully snaps to this nearest discrete item. This mapping transforms our messy continuous matrix into Z sub Q, a neatly quantized representation. By forcing the data into this discrete space, the model is compelled to identify solid, meaningful features that explain the classifier's behavior, rather than getting distracted by irrelevant noise. Finally, this quantized matrix Z_Q is passed to the decoder. The decoder's job is to reconstruct the image, but with a twist. Under the pressure of the loss function, it pushes as many irrelevant pixels as possible to black, generating a sparse explanation. This sparse image is then fed into our target classifier. Because the discrete dictionary captured the most essential features, the classifier confidently screams, "Dog, 93%. We have successfully generated a sparse, confident explanation, all thanks to the power of a discrete latent space. The true power of SpaCE-VAE does not just lie in its architecture, but in this elegant mathematical equation. Let's write down the full objective function. At first glance, it might look intimidating, but if we break it down and move it up here, we can see exactly how each term sculpts our final explanation. Let's focus on the first two terms. Together, they form the VQ-VAE foundation. The commitment term acts like a magnetic force. Watch this vector. It forces the continuous data to snap directly onto the nearest concept in our discrete dictionary. Meanwhile, the reconstruction term scans the image, trying to redraw our dog. Notice that during this process, some minor background pixels at the edges naturally fade to black because the dictionary only keeps the core structural information. But the dog itself is perfectly preserved. Now comes the destroyer, the third term, the L1 norm, multiplied by alpha. In optimization, L1 is famous for enforcing sparsity. Think of it as a relentless vacuum cleaner, forcefully sucking the intensity of every pixel towards zero, which means black. As it begins to aggressively black out the pixels right in the center, the very body of the dog, disaster strikes. Look at the confidence gauge. By destroying the pixels that define the dog, the classifier is blinded. Its confidence plummets from a robust 93% down to a mere 12%. If left unchecked, alpha would turn everything pitch black. That is where the final term steps in, subtracting beta times the cross entropy. This is the classifier fighting back. It acts as a strict gatekeeper. It sounds an alarm and forces the model to recover the exact pixels that caused the confidence drop. Watch as the pixels forming the dog's eyes and snout are lit back up, rescuing the confidence gauge back to 93%. What you are witnessing right now is a mathematical tug-of-war. Alpha pulls towards darkness for a sparse image, while beta pulls towards the light to preserve the model's confidence. The equilibrium of these two opposing forces is exactly the optimal, sparse explanation we are looking for. The equation is beautiful, but does it work in practice? Let's put SpaCE-VAE to the test on the SciFAR-10 dataset. The authors evaluate sparsity on two fronts. The left graph shows L0 norm sparsity, which simply counts the percentage of pixels completely blacked out. The right graph shows L1 norm sparsity, measuring the total reduction in pixel intensity. Now, look at traditional attribution methods like deep lift, integrated gradients, or feature ablation. To make the image sparser, they rely on a forced threshold to mask out pixels. The consequence? By removing just 10 to 20% of the details, Their accuracy crashes drastically to below 30%. But now, look at SpaCE-VAE, the red line. Notice that it is not a long, sweeping curve, but rather a short, floating line segment. This is not a bug. SpaCE-VAE doesn't use any forced manual thresholds. Sparsity you see is an organic evolution from the neural network as we adjust the protection force, beta. Even though it's a short segment, it proudly demonstrates that the model automatically discards up to 50% of the intensity under L1, while keeping its accuracy rock solid above 70%. An overwhelming victory. Yet, no mathematical model is perfect. The authors frankly point out a critical blind spot in this algorithm. SpaCE-VAE uses the L1 penalty as a vacuum cleaner to force irrelevant pixels towards 0, which corresponds to black. But what happens if the object itself is already dark, like a dark-colored dog standing in front of a white-tiled wall? When the L1 penalty blacks out the bright background, it unintentionally wipes out the very contrast needed to define the dog. The dark dog completely vanishes into the pitch-black background. The simplicity of mathematics sometimes betrays the semantics of human vision. Despite this limitation, SpaCE-VAE introduces a radically new mindset for explainable AI. It proves that a truly good explanation doesn't just mean coloring over the original image, but knowing how to let the model discard the noise while maintaining its confident core. Thank you for watching, and see you in the next equation.